Let's take a look at our free particle solutions and decide whether we have acceptable wave functions or not. We have two situations to think about. We have the case where the energy is greater than the potential, and this would be classically allowed regions. So you'll recall that our wave function, when we have e greater than v naught, is going to be imaginary. So it's c1 e to the ikx plus c2 e to the minus ikx. And that describes our classically allowed. When we're in a classically forbidden region where e is less than v naught, then we have the real wave functions. And so we can write psi at x for this situation as c1 e to the kx plus c2 e to the minus kx. We need to make sure that these functions are continuous, single valued, and finite. And in addition, we need to be able to normalize these functions, so they have to be normalizable. So if we think about what these traveling waves look like, they're basically sine waves. And so we can draw a snapshot of that wave that looks like this. And we can see that this function is continuous. It doesn't have any breaks. It's single valued. It only has one value of the function for each value of x. And it's finite. It never goes to infinity at any place. So now we need to decide whether we can normalize this function or not. And remember that normalizable means that 1 is equal to the integral over all space of psi star psi dx. So psi star, remember, is replacing each of the i's with an I of the opposite sign. So we have c star 1, because our coefficient could be imaginary, minus ikx, c2 star plus ikx, because we've just changed the sign of I in each instance. So if I take psi star psi, I'm going to take my function for psi star, as written above, and I'm going to multiply by my function for psi. So that will be psi star psi. So you'll see that I have to FOIL this, right? So I take c1 star times c1 times e to the minus ikx times e to the ikx, but e to the minus ikx times e to the ikx is just 1. And then when I do the c2 star times c2, I get the same thing, because e to the ikx times e to the minus ikx again just equals 1. Then I have cross terms where I have c1 star times c2, and then those are both e to the minus ikx, so I end up with e to the minus 2 ikx. And then my other cross term is c1 star times c1, and both of those are e to the plus ikx, so I end up with e to the 2 ikx. So now I need to integrate this function from minus infinity to infinity, because x can go all the way from minus infinity to infinity over all x's. And if I choose C1 and C2 correctly, then the idea is that this will equal 1 if it's normalized. So I'm hoping to be able to pick a C1 and a C2 such that this equals 1. Well, C1 star times C1 star and C2 star times C2 star are constant, so they come out of that integral. And then the integral of dx is just x, and I'm evaluating from minus infinity to infinity. And then I have the other two terms in my integral as well. But let's just look at this first term to start with. So you'll notice that if I put infinity in for x, I get infinity. And then minus infinity in for x, I get a minus infinity is infinity. And that sums up to 2 infinity times my coefficients. And that can never equal 1. And so this function is not normalizable, and I'm going to have to figure out a way to fix up this classically allowed free particle wave function in order to get a normalizable wave function. Let's take a look at our classically forbidden solution. Let's take each of these basis functions separately and think about what they look like. So if I graph e to the kx, positive kx, then I have something that asymptotically reaches 0 for x less than 0, but is infinite, so that it goes to infinity for x greater than 0. So this first part of the wave function is only acceptable if x is less than 0. Now let's look at the other part of that wave function. So if I graph e to the minus kx, it will be 1 when x is 0, and it will asymptotically go to 0 at large x and infinity at large negative x. And so it's acceptable for x greater than 0, but if I put in less than 0, then it's going to go to infinity. So this part of the wave function is only acceptable for x greater than 0, and this part of the wave function is only acceptable for x less than 0. So if we look at each of these functions, we can see that they are continuous, both of them. They are both single-valued. They are finite if we look in the right regions, right? So finite, we have to be careful. We can use e to the kx for x less than 0, and we can use e to the minus kx for x greater than 0. Okay, so that will all work fine. And then we need to see if we can normalize these. So can we normalize these functions? So to normalize them, we're going to need to normalize them on their respective intervals. So let's think about the first one. So we have minus infinity to 0 of c, c1 squared e to the 2kx dx. And when I integrate that, I get c1 squared over 2k e to the 2kx, and I evaluate from minus infinity to 0. And when I put 0 in for x, e to the 0 is 1, so I get c1 squared over 2k. And when I put minus infinity in for x, e to the minus infinity goes to 0, and so this is equal to 1, and as long as that's equal to 1, I have a normalized wave function. So c1 can be equal to square root of 2k, and then my wave function is normalized. So that's normalizable. And I can do the same thing for the other one, and I can show that it is also normalizable with the same normalization constant. So these wave functions in the classically forbidden region are acceptable wave functions as long as I make sure that I'm using the right form of the right basis set for the range of x's that I'm interested in.